Hola a todos, mi nombre es MK. This is Spanish. I'm gonna do one language per day. Hello everyone. My name is MK. If you like my explanations, please like and subscribe and explain and also introduce my channel to your friends. Your support means a lot to me. I'm trying my best to give you the best explanation so it's easier to understand for everyone. Today's problem is a hard one, but it's interesting. It's quite an interesting problem. For an integer array nums, an inverse pair is a pair of integers I and j such that I is less than j and num I is greater than num j. So that is why it's called inverse pair. We are given n and k, and we should return the number of different arrays that consist from 1 to n. From 1 to n, this is important, such that there are exactly k inverse pairs. Exactly k inverse pairs. Since the answer can be huge, we should return the answer modulo 10 to the 9 plus 7, which is a big prime number. So far, we have two things, one definition, and the other one is that we are dealing with permutations. So whenever you see from 1 to n, there is a chance that permutations are related. So let's keep that in mind for now. Let's look at the example. So n is 3 and k is 0. What does that mean? That means 0 inverse pairs. That means no one is bigger than a number that comes after that. That means all of the numbers are in increasing order, 1, 2, 3. So there's only one permutation that looks like that. Example 2, n3, k1. So that means there should be only one number that is bigger than a number that comes after that. So 1, nothing. 1 is not bigger than any other number. In this case, 3 is bigger than 2. So the number of inverse pairs in this permutation is 1. In the other permutation, 2 is greater than 1. So this is the only inverse pair here. The other, like 2 and 3, is not inverse pair. 1 and 3 is not inverse pair. Let's go and see how we actually can attack this problem. The only thing we have so far, as I said, is the definition of inverse pair and the fact that we are dealing with permutations. So let's say you have all the numbers from 1 to n, and you want to create a permutation. So how do we create a permutation? How do you, like, one number at a time? One number at a time, we can create a permutation. So, but here we are talking about f of n and k. I just gave it a name, the function f of n and k. That is what the problem is asking us, n and k. So this is not hard. We have this function. We should solve the problem for n and k. So one number at a time, we create a permutation. So this is a permutation. Let's say we pick number 7. Let's say we have n options, right? 1, 2, 3 to n. Let's say we pick number 7. What happens here? We know the numbers 1, 3, 2, 6, 5, and 4. We know all of them are going to come after 7. We know that because we took 7 and put it at the first place. So the other 6 numbers are going to come after 7. And all of these are inverse pairs, right? So if we pick 7, we will have 6 inverse pairs. And so in general, if we pick I, we will have I minus 1 inverse pairs. Sounds good so far? So I minus 1, this number is important actually. And I goes from 1 to n, right? I goes from 1 to n. So that means we can, so what do we do with the rest of the numbers? So the rest of the numbers are n minus 1 of them. So after we pick 7, we have n minus 1 numbers. So after we pick generate k minus 6. We should generate k minus 6 inverse pairs. Oh, interesting. So now we should just count this number, f of n minus 1 and k minus 6. So this is when we pick 7. What about other numbers? Let's try other numbers. So if I pick 6, it's going to be f of n minus 1 and k minus 5. If I pick 5, it's going to be f of n minus 1 and k minus 4, and so on. F of n minus 1 and k minus 3, and f of n minus 1 and k minus 2. So this is 4, 3, and so on. So let's just write that as a summation. So f of n and k becomes summation of I equals 1 to n, f of n minus 1, because we get rid of one of them, and k minus a minus 1, which is k minus I plus 1. So again, let me reiterate this, that when we pick one number, we have a smaller subproblem, and that a smaller subproblem has n minus 1 numbers and k minus I minus 1 inverse pairs. And this is exactly like the original problem, but it's with a smaller limitation. So we could break the problem into a smaller subproblems like this, and we can solve this. The reason we can do it is that from 1 to n, we can rearrange them and look at them as if we have numbers from 1 to n minus 1. It doesn't matter. It doesn't matter. What mattered was these arrows, which we counted. We counted the number of inverse pairs, and now we have a smaller subproblem with n minus 1 numbers and k minus I plus 1 inverse pairs. That's why we can write it like this. So here the running time of this is going to be O of nk, because we have nk states. We have nk states times this for loop, this summation for loop. This is going to be n. So in general, it's going to be O of n squared and k. And since k is going to be as big as n, you can assume that this is n cubed, but it doesn't matter, n2k or n cubed. These are both of them are bad. You can because the constraints are 1000, and when constraints is 1000, this is going to become in order of 1 billion. And as a rule of thumb, whenever you calculate this number and put the upper bound of the constraints, if it's in the order of billions, it's probably not good. It's probably not good. So how do we solve this? How do we fix this? Let me get rid of this. So, okay. So at the next step, we should think how we can improve this. How we can improve this. So the number of states is fixed. We cannot do anything about it, but maybe we can do something about this. Maybe f of n and k can be explained, can be written as a few clauses instead of a for loop. Okay, but how do I know that? So if you look at this, f of n minus 1 and k minus I and plus 1, this is actually using some small subproblems. One technique is to take a look at immediate subproblems of f of n and k and see if you can find any overlapping subproblems with this one. So we are looking for overlapping subproblems. Okay, so here the immediate, sometimes we should go further, not just look at the immediate subproblems, But let's look at the immediate subproblem. So the immediate subproblem is going to be f of n minus 1 and k, or f of n and k minus 1. And if you write this is going to be sum of I equals to 1 up to n of f of n minus 1, n minus 2, n minus 2, and k minus I plus 1. And if we write this is going to be f of n minus 1 and sum of I equals 1 to n, f of n minus 1 and k minus 1. Okay, just put k minus 1 instead of in place of k everywhere in this formula. So this is our formula. Put k minus 1 everywhere. So this is going to be n minus 1 k minus 1 minus I plus 1. So this is going to become k minus I. Okay. So now if we compare this one with this one, we will see that they have some common subproblems, because both of them are n minus 1 and some, other number. But this one is n minus 2, so they don't have something in common. So we should go and further explore the possibility of overlapping subproblems between these two. I'm going to write f of nk again. So f of nk is going to become sum of I equals to 1 until n, f of n minus 1 and k minus I plus 1, right? K minus I plus 1. And the other one is going to be f of n and k minus 1, which is going to be sum of I equals 1 to n, f of n minus 1 and k minus I, right? N minus 1 and k minus I. So let's go ahead and expand these two. Let me see if I can do it here. All right. So I'm going to expand this one first. So if I is equal to 1, it's going to become f of n minus 1 and k, right? If I is 1, it's going to be k minus 1 plus 1. Plus. So as I grows, this number here gets smaller. So this is going to be f of n minus 1 and k minus 1. Plus f of n minus 1 and k minus 2 plus, when we put n here, it's going to be f of n minus 1 and k minus n plus 1. K minus n plus 1. This is the upper bound of this summation. Let's write the other one here and see what we have in common. This is going to become f of n minus 1. So if we put 1 here, it's going to be k minus 1. K minus 1. Okay. Plus f of n minus 1 and k minus 2 plus f of n minus 1, f of n minus 1 and k minus n, right? So here, that's interesting. There are some numbers in common. So for example, f of n minus 1 and k minus 1, they start here and they go all the way to f of n minus 1 and k minus n. But this one doesn't have it. So the next number is that. So let me write this. So this is basically f of n and k, right? So I'm going to add something to both sides of the equation. And that something is the missing sentence. So f of n minus 1 and k minus n is missing. And that is the next one here. Why? Because we said this is decreasing, right? This is decreasing. So the next one here is going to be f of n minus 1 and k minus n. So if I add this to both sides of the equation, plus f of n minus 1 and k minus n. Okay. Now I will add it to the other side as well. So plus f of n minus 1 and k minus n. Awesome. So now the right side of the equation here, this is not the right side, sorry, from here. Yeah, from n minus 1, this part, n minus 1, k minus 1, n minus 1, k minus 1, all the way to n minus 1, k minus n, n minus 1, k minus n. So this part is going to become, f of n and k minus 1. You see, f of n and k minus 1. Okay, so we have this plus this. So in order to have f of nk, we should just move this sentence to the other side of the equation. So f of nk, n and k becomes f of n minus 1 and k plus f of n and k minus 1 minus this one, because we moved this to the other side of the equation. Okay, that's great. So we could write this f of nk in terms of 3 different subproblems. It's not a for loop. So now the running time becomes O of nk, because this is constant. We are just adding 3 numbers. Let's go and see what are the base cases. The very obvious base case that comes to your mind should be like permutation, right? So permutation n equals 1. So when n equals 1, this is simple. If k is 0, that means you have one answer. Return 1. Otherwise, return 0. Otherwise, what does that mean? That means n is, for example, n is 1 and k is 2. What? What do you mean? Like a permutation of length 1 and 2 inverse pairs? That is impossible. Return 0. Okay, in any other case. And the other one is because we are doing this. Because we are doing k minus n, this could get negative. So the other case is if k is less than 0, this is definitely return 0. It's impossible, when this is negative. And that's it. Let's go and see how we can write this code. The code should be simple because of this. This is a dynamic programming problem. We are going to memorize the answers, so we need a DP table. And we need a function. So here we are just going to initialize the DP. So it's going to be n plus 1 of them and a vector of int that is of size k plus 1 and negative 1. And that's it. We return f of n and k. Now here, the base case, remember what does the base case? If n is 1. If n is 1. If k is 0, return 1, return 0 otherwise. Okay. And if k is less than 0, return 0. And otherwise, we should just calculate the result. So we need to return the answer mod this number, modulo. So we define that. So this is our number. This is a prime number. Okay. And here we should check if this subproblem have been calculated or not. So if dp of n and k is not negative 1, return dp of n and k. Otherwise, dp of n and k becomes what's that? The recursive formula of f of n minus 1 and k, f of n minus 1 and k plus f of n and k minus 1 f of n and k minus 1, and we do it mod like this. Then we should subtract n minus 1 k minus n. So dp of n and k equals dp of n and k minus f of n minus 1 and k minus n. But because we are subtracting something from this number, this could get negative when we do a modular operation. So we should say if dp of n and k is less than 0, we should just add mod to that. dp of n and k plus equal mod. So think about why this is correct. So this means like after this line, dp is a number between negative mod minus 1 to mod. So it's like the absolute value of dp of nk is less than mod because we did a modular operation here. So if it's less than 0, we can just add a mod to that and it will become greater than 0, but still it's gonna be less than mod. Okay, think about this. And if you have questions, ask me in the comments. That's it, and then we return dp of n and k. Let's see if this works. Yes, let's try a big test. So 1,000 and 1,000 actually. And run. Okay, this works. Let's submit. Okay, that's it. Let me know what you think about this approach and how I explained it. Like starting from a permutation, choosing a number, and then finding the recursive formula. So f of nk becomes n minus 1 and k minus 1. This is the recursive formula, but this is not optimal because of the for loop, because of this summation. So then we try to find an immediate subproblem of f nk and make it more simpler. F of nk now becomes this. Let me know if you have any questions in the comments. Thank you.